So first I will go through the question. This question is actually related to KTG, and in this question we have to also apply a concept related to circular motion dynamics. So what all things here we can see is that there is a tube. This is a tube. It's a cylindrical tube, and it is doing circular motion about this axis like this. So this is I will make one drawing by myself. This is the tube, and it is rotating like this. It is going in circular motion like this in horizontal plane. So both the end of the tube they have given that the molecular weight of the gas is capital M. It is rotated in horizontal plane with angular speed omega. Angular speed is omega. The axis AB is perpendicular. The axis perpendicular to AB. This is AB, A and B. This axis is perpendicular. That means this axis is vertical. This axis is vertical, and this tube is doing circular motion in horizontal plane. Now what we have to find in this question is actually we have to prove this thing that pressure at B is equals to pressure at A into exponential of m omega square L square by 2 RT. Here they have given that temperature will be same at all the points. Okay, that means they are in this question they are saying that pressure at B and pressure at A both of them are not same. This kind of question we actually encounter this type of question in fluid mechanics, where in the tube a fluid is filled, and then we have to find the pressure difference across its ends. But here there is a basic difference. The difference is that in fluid mechanics when we say that fluid is incompressible. Fluid is incompressible. That means fluid cannot be compressed in most of the cases. Here we are encountering a gas, we can say ideal gas. So ideal gas, that means we all know that ideal gas is compressible. So we cannot handle this question in the same way as we deal in fluid mechanics. This we will see first. If you want to try this question by yourself, you can try this. You can pause the video and you can try this question. Now I am going to solve this question. First what we have to do is this in this tube we can find gas molecules at every places, distributed at every location, at every place. These are the gas molecules that I am drawing. Now what happens is that this all the gas particles, all the gas molecule, they all of them are doing circular motion. Every gas molecule is doing circular motion. And if every gas molecule is doing circular motion, that means they need some centripetal force, any centripetal force. If any particle is doing circular motion with constant omega, one force is required, that is centripetal force. And second important thing is that every particle is doing circular motion with different radius. Every gas molecule does circular motion with different radius. So the radius is different for every particle. Difference in radius, that means if we apply the centripetal force equation, we will write that sum of all the forces toward the center should be equals to m omega square r. But here r is variable. That means now we know that we have to apply differentiation or integration. So we have to apply integration in this question because here r is variable. We cannot directly apply this formula. So let us proceed with this thought. what we can do here is so the radius for every particle is different. So what I can do is I can go x distance from the axis, and I will take a small element of length dx. So this is length dx, and for dx part we can say that the radius of circular motion is x for this dx part. So if we will consider this dx part, this is doing circular motion like this, and if it is doing circular motion, that means there is some net force towards the center. So what force we can say that this part is experiencing? This part is experiencing only forces, like I can say from the tube in this direction or this direction, or I can say that from the gas of the left side. So here consider some force here, that is another force. So this right side force will be greater than left side force, because this part has acceleration towards the center. Centripetal acceleration is towards the center, so net force will be towards the center. That means I can clearly say that this pressure from this pressure and this side pressure, we can say that right side pressure is high and left side pressure is low, because this part is experiencing net force towards the center. So here I can take pressure as P. Here I am taking pressure as P, this side. Here then if this side pressure is P, here the right side I can take pressure as P plus dP, a small, very small increment of pressure. So if I will draw the FBD for this small elemental gas part, from here it is experiencing a force of P plus dP into area of tube. From here it is experiencing force of P plus P into area, P into area. So what I can say is the net force towards in horizontal direction towards the center is P plus dP into area minus P into area is equals to dm. Dm means very small mass of this dx length, dm omega square, and the radius for this part will be x. We have taken here this as x. So for the radius for this part will be x. Now I can say that dp into area is equals to dm. Dm I can write mass is equals to density into volume. Volume I can write area into dx. So this part I can write rho a dx omega square into x. Now this area gets cancelled. dp is equals to rho omega square x dx. Now here comes the important part. If I am writing like this, that a small change in pressure is equals to density omega square x dx. Now in this case, if I will consider this as ideal gas and the pressure everywhere is different, that means I am saying that it is compressible. The ideal gas is compressible. So that means density will be different. If the pressure is high somewhere, the density will be higher. If the pressure is low somewhere, that means the density will be lower. That means here density is variable. This quantity is also variable. This quantity is also variable, and pressure is variable. So that means now we have to somehow establish a relationship between pressure and density, and we know that we can use ideal gas equation for that. We know that PV is equals to nRT. PV is equals to nRT. That means P, we are taking this for this small section of gas, so P into dV is equals to n. N means mass of the gas, dm divided by molecular mass into RT. From here we can clearly see that P is equals to dm by dv RT by capital M. From here we can say that P is equal to dm by dv is nothing but density, rho RT divided by capital M. So from here I can say I am getting a direct relationship between density and pressure. In the question they have given that temperature is constant everywhere. Here you can see that the temperature is same at all the points. So that means here only two variable, density and pressure. So I can simply put this density formula from here in this part, and what I will get is dP is equals to P m divided by RT omega square x dx. Now in this equation we have only two variable, pressure and x. Now I can integrate this equation simply. What I will get here is dP divided by P is equals to m omega square x dx divided by RT. We know that from lower limit to upper limit we will integrate both the sides. Lower limit is this point A, upper limit is this point B. So if I will take this point as lower limit as A, upper limit as B, lower limit A, that means here pressure is PA, point B pressure is PB. Lower for initial point x will be equals to 0, for point B x will be equals to L. So here you know that 1 by x integration will be ln x. Here I can write ln PB divided by PA is equals to, now here m, r, t, omega, everything is constant. X integration will be x square, you will finally get nothing but L square by 2. From here I can say that simply PB is equals to PA into e to the power m omega square L square divided by 2RT. So here there were three important point which I like to highlight in this question. First thing is that here for ideal gases, if pressure varies, that means the density will also vary. For every point density will be different, it will not be constant. And second thing is that here first circular motion concept will be applied, and if there is gas, we know that most of the cases, if gas is there, we have to apply ideal gas equation. So we have to apply, we have used ideal gas equation. So that means we are getting our answer as we have proved this formula that PV is equals to PA e to the power m omega square L square divided by 2RT. So if you have any doubt, you can comment or reach out to me for this question.